force applied to the electrons is a small radiation is here. On the other hand, the electron speed is very close to the speed of light. The sharp and coherent X-rays is produced of these directions. It is the same picture of magnet in the X-rays. So the first original one is a bending magnet. Just one magnetic system is here applied to the one set of the magnet. In this case, the wavelengths distribution of wavelengths is like that. This is the lambda means divided by the Compton scattering length. And here is the top of the peak of the the Compton scattering. This is a critical scattering wavelength. So it has such structures. Of course, this is a wavelength, the low energies, and this is the high energies. So it's a critical energies. The critical wavelength is calculated by these equations. R is the radius of the storage ring, and E is the energy of the ring operation. And here is another structure of the function of X-ray energies. So the critical energy is increasing. So as a function of photon energies, like that. If we compare the synchrotron radiation facilities, this critical energy or critical wavelength is important parameter. Second one is the insertion device. Abbreviation is IDs. This type is the wigglers. When the bending magnet, the one set of the magnets is set here, but there is a similar magnets alternatively located, and electrons going like that. So in this case, the X-rays is go here, go here, go here, and some compared to the bending magnet is like that, and wiggler is the more strong brightness and high energy as obtained. Another insertion device is the undulator. A more narrow and more high number of magnet electrons go to the very fast alternatively, so the almost front directions X-rays come in. In this case, the very high brilliant X-rays is obtained from the first and third, fourth harmonics. Some kind of experiment, the continuous spectrum of X-ray is very useful. In this case, brilliance is flux is very high, but it is not continuous. It's a periodical state. In such a device, we control to the width of this magnet changing and move to the higher harmonics. Now we summarize to the bending magnet is here, and some wiggler is here, and undulator is like that. This is an example of the ESRF in France. Here is a photo of the in front of the wiggler and it's undulator. The electron is coming from backside. Now, second section, we move on to the interactions of X-rays with matter. Of course, X-ray is an electromagnetic wave. So in the matters, there is many electrons. This interactions is actually the electric wave, electric vector, and electrons. This is a photo from the Röntgen wife. In that case, the X-ray is, what is X-ray? Nobody knows the dangerous or beneficial or some effect of the X-rays. This is a very crucial photo. Now, there is matters, the many electrons inside, bounded in the inside the matters. X-ray coming of this way, and some interaction, there are some interactions like that. First simple interaction is Thomson scattering. Another name is elastic scattering. The same electrons, same energy is scattered, emitted. In this case, and another one is in elastic scattering. We call the Compton scattering after the name of the physicist. And the green one is concerning to the absorption process, photoelectric absorption process. And the red one is the scattering process. For the photoelectric absorption process, the emitting the photoelectron is the primary phenomenon. Another one is fluorescence detection, fluorescence emission. The last one is secondary electrons emissions. We call the OJ electrons after the physicist, name of physicist. So, roughly speaking, the main process is the scattering process and the photoelectric absorption process. After the resulting this process, we measure the beam attenuation after the matters. Now we discussed the Thomson scattering. Simply speaking, in Thomson scatterings, the one electron is located at the origin of axis here. And the X-ray is coming left-hand side, from left-hand side, and moving the electric wave. So, one electrons moving the same frequencies, and after that, the emitted to the secondary X-rays with the same frequency. So, the incoming direction is this Z directions, and outcoming X-rays is all over the angles, except for the only your directions. This is more accurate explanations. No Thomson scatterings to the direction of electron moving. Why? Compton scattering not going to these directions. The X-ray wave is a transverse direction wave. Transverse is okay. Transverse. Longitudinal is longitudinal. It's complicated. My English is not so good. So transverse. So if the X-ray is coming to the X wave, X directions, electromagnetic wave should be the longitudinal moving. That is the breakdown of the relativistic principle. So from the physical aspect of this Compton scatterings, the X-ray is just like a rose, and electron is like a target. So the scattering cross section is expressed as the area of electrons. That means it has a dimension of length. It's about such values, and it depends on the cosine phi. It means the direction of Thomson scattering is shadows of these directions. So no more 90 degrees to the direction of X-rays. You can calculate it of these values in the tutorial of this after these lectures. And next talk is the Compton scattering. Compton scattering is like a billiard. The photon is coming this way and pushed up the electrons go this way. So the momentum transfer is occur, and some another photon goes another direction. So we can solve all these systems using the relativistic theories of the energy conservative and momentum conservative. Final result is like that. The energy of scattering versus incident scattering is depending on the scattering angle. So forward scattering, in the case of the forward scatterings, the energy of Compton scattering is the same as the incident X-rays, but this is just one. And the changing the angles, this scattering energies degrees, and it depends on the angle and depends on the incident X-rays. That is the profile of the detection of X-ray Compton scattering. The zero forward scatterings, the same as Thomson and Comptons, and some degree of is more. Some degrees, and Thomson is here and Compton is here. This is a wavelengths, the lower energies or longer wavelengths, and another larger angles and larger angles like that. Now we move on the absorption coefficient. There are three effect, three behavior in the absorption coefficient. First is the photoelectric absorption. Second is fluorescence. Third is the secondary electrons. This is just simple considerations of the emitted photoelectrons. And here is the experimental expectations. Energy of here and X-ray, absorption coefficient or absorption cross-section. Absorption coefficient is the parameter of the experimental setup, and cross-section is from the theoretical physics. So it depends on the force of atomic number and minus third of X-ray energies. This is an interesting demonstration of the experimental data. The cross-sections is normalized as energy third, and third of energies and minus fourth of atomic number from the aluminum, iron, krypton, silver, lead. The same first we see the after these normalizations, no dependence of energies. So it shows the energy dependence is the third of energies, is a straight line. And another one is there is a coincidence of the such kind of several atoms, here and here. This means the cross-section depends on the Z force dependence. So in our systems, X-rays and elements are interacted of this energy dependence and atomic number dependence. The detailed X-ray absorption process. First one is already show you the photoelectron absorption. For example, K-shell excitations, electron located at the K-shell is excited by the X-rays go to the continuum state. This is the K-shell photoelectric absorption. In the case of the fluorescence emissions, once emitted to the K-shell, so vacant exists on the K-shell. So relaxation is occurred from the L or M, the upper side of electrons. The subsection of the difference of electrons goes to the another X-rays. This is a fluorescence. This is called to be fluorescence. In case of from the L level, we call K alpha. In case of the electrons come from the M level to K level, we call the K betas. OJ electrons, the same as the vacancy exists in the K edge, K level. The relax is occurred, but this X-ray energy is converted to the excitation to another electrons from the M edge. This is secondary electrons is going up. And the energy scheme, atomic scale is here. K level, the electron orbital is 1s. For L shell, 2s, 2p, 2p. 2p is there are two types of 2p's separated by the spin orbit coupling. This spin orbit coupling is very important to the discussing of the XMCDs, X-ray magnetic circular dichroism. This is an important magnetic analysis using a synchrotron radiation. Another one is the MH. There are 5 levels exist in MH, and some saying spin orbit coupling is around here. It is here. Finally, we summarize the process of the structure analysis using the X-rays and compare to the neutrons. Using the this is roughly speaking the scattering of the X-rays produced to the X-ray diffraction method, and spectroscopic way to using the X-rays means X-ray absorption structures. In this case, X-ray diffractions, the long-range order are necessary in the crystal state. On the other hand, the case of X-rays, I show you the later more details. The very short X-ray electron mean free path is important. So the short range order is enough to the in the solid. So amorphous solid or liquid state or some nanoparticle is very effective to the measurement of the X-ray. Neutron is also used by the neutron diffraction method as a process of the neutron scattering. So this is a simple first order effect. Of course, now the situation is improved using the third generation synchrotron radiation facilities. Some kind of resonance or non-resonance scattering and combined by the X-rays. For example, the excited X-rays tuned at on the edge. So another scattering information is coming. And from the neutrons attract or neutrons interact to the magnetic system directly. So there are several branches of the material science, but it's a more simple picture is summarized like that. Now, that is the end of the lecture second. I prepare the tutorial time. So here. How do you play to the tutorial? Is the calculation of your notebook? I have no detailed information for the tutorial. I prepare the several problems related to in these sections. We try to calculate, or some this discussion is first we discussed in these sections. Thomson scattering length calculation, calculated Thomson scattering length and Compton scattering length, and compare it is very interesting to the Thomson scattering and Compton scattering and Bohr radius. It's very important the relation to the fine structure constant alpha, or some technical problems, conversion from the wavelength to electron volt. This is the typical value of what is a critical length. Lambda c is example of the R20 meters and 3 giga electron volt for bending magnet. And this is also a very simple problem for you, but energy of mass electrons, rest of mass electron is one typical and critical values. So we discussed after the question or comment. Okay, if you have a comment or discuss questions in this X-ray. Yeah, X-ray lecture second. For synchrotron radiation facilities, we have all the second generation facilities named photon factories, but it's still active, so because of the sophisticated maintenance. And after that, we have a spring 8, the large energy, the big energies, the 8 giga electron volt operations. And after that, Japan has a plan to the new treatment of the 3J beamline synchrotron radiation facilities, because the 3J is very high brilliance and sharp X-rays in the intermediate energies. So now the science is focused on such kind of intermediate tender energy regions or intermediate regions. And I forgot this. This is the absorption edge is concerning to the X-surface. For the excited electron from the KH, the big one sharp. There is one sharp absorption edge here, because the 1s level is single. Secondly, is the L edge called L1, L2, L3. The absorption edge is separated by 3. And the M edge is separated by 5. But actually, this is separated by the 5 step functions. And this background includes to the excited the electrons another level of electrons, and this edge has a background of the more higher energy of lower energy of excitation energies, excitation cross section, and so on. M edge the background includes to the cross section more lower energies. So in this K edge includes the all of lower energy cross sections. This is the structure of absorption edge. You are familiar to the X-surface? Oh, good. Any question or comment? No? So try to solve the quiz. Yeah, you can take a memo for the, this is the Thomson scattering length. And another one is the, no, Compton scattering length. I have no information for the Compton scattering length. Do you know the equation of the Compton scattering length? Okay. Idea in pencil. Just exercise. Yeah. Put on the blackboard. Don't you have a note of this sheet? No. Print out it. Print out this note. No. But what is it?
Cluster of the nanoparticles.
Cluster of nanoparticle? No, what your question is?
Cluster of nanoparticles. Cluster of nanoparticles. What are the cluster of nanoparticles?
Yeah. Cluster is more smaller size. Just a few atoms in the clusters. Nanoparticle is more larger, but length of the diameter of something nanometer order.
If they are in the number of atoms and number of particles.
Number of several number of the atoms we call cluster.
Randomly anyone two atoms, two particles, four particles.
That's right. That's right. Yeah. Clusters. That is cluster.
How we can explain number of atoms and number of particles? Then these are random.
I don't know that it's a critical numbers, but the smaller one is clusters.
They can learn to the same number.
Oh, here. Can you check from the internet? Find the internet. Yeah. And the ratio of the lambda c. This is R0. And R0 lambda c. And lambda c or Bohr radius should be alpha. Check the should be alpha or alpha inverse. I don't know. Interesting result. Nobody knows. Here is the first quiz, first exercise of in the tutorial. And これはいるな。これか。The lambda c is different of the lambda bar c. Lambda bar c is a Compton scattering. The lambda c is a critical wavelength. 5.6 meter and A J. Holy boom. It's okay? Tutorial. Training of the